We're going to look at the first Practice FRQ for the Chapter 16 Chemical Equilibrium Problems. Now, when we see this graph, this should remind us about what happened when we did the straw lab, because in the straw lab, we started off with water in one of our two containers, and it went down, and at the same time, then something with our products was going up. So we're going to have some kind of a situation like that and say, equilibrium is when this levels out. So let's see how this actually plays out for this problem. It says after 1 mole of sample of HI is placed into an evacuated 1 liter container. So if we have 1 mole in a 1 liter, then that's going to be a 1 molar solution at 700 Kelvin. The reaction represented above occurs. The concentration of HI as a function of time is shown below. Now, this temperature is not critical. It's not something we're going to have to really actually worry about usually. It's proper to say this happens at this temperature, something else happens at a different temperature. The actual first question, write the expression for the equilibrium constant Kc for the reaction. Well, we can do that. Now, a lot of times these problems start off with something kind of simple, and they say that's the accessible point. So we're going to say, well, Kc is products over reactants. So it's the concentration of H2 times the concentration of I2 all over the concentration of HI squared because of the 2. And be very, very careful. If there's any mistake that I usually make on these problems, I forget to square that number. Now that's part A, so far so good. Part B, what is the HI concentration at equilibrium? Well, we're actually going to get that just from our graph, and we can see what happens here. We're ending up, so we say, do we know what equilibrium is? Equilibrium is when this thing settles down, so the concentration is 0.80 moles per liter. HI concentration 0.80 molar. Now determine the equilibrium concentrations of H2 and I2. Well, we know how to do that, so that's an icebox problem. So we started off here with the idea we had 1 molar HI to start with, and at equilibrium we're down to 0.80 molar, so we must have used up 0.20 molar. Now, if we are using the HI, we must be forming H2 and I2. Now, here's the important part, and that is, watch out for this is a 2 to 1 to 1 ratio. So if we use up 0.2, we must be making 0.1 moles per liter of the other two chemicals. So 0 H2 to start with, we make 0.1. So at equilibrium we have 0.1 and 0.1 of our H2 and I2. So here's our equilibrium values of all three chemicals. Now we're going to go back and say, okay, on the graph above, make a sketch that shows how the concentration of H2 changes as a function of time. H2 is 0.10 molar. So we're saying as this reaction goes, we're going to end up with 0.10 molar. So when the HI concentration is 0.8, this becomes 0.1. So starting from 0, it's going to come up to 0.1. So we're looking for, are you starting at 0? Are you ending at 0.1? Because since it's a 2 to 1 ratio and only make half as much of the HI. And then do we draw a nice line that gets us there. So we've answered this question. On the graph above, make a sketch that shows how the concentration of H2 changes as a function of time. So far, so good. Now part E, calculate the value of the following equilibrium constants. So Kc, now we know Kc from before. Okay, Kc is HI concentration times I2 concentration over HI concentration squared. Substitute in our values, and when we do that, I get a value of 0.015625. Now this would be a convenient time to put this in scientific notation. So I'd say 1.6, because it's 5/6, times 10 to the negative 2. And I round it off to 2 significant digits because all our concentrations are 2 significant digits. Now the second part here says, well, what about Kp? Well, we know that Kp is equal to Kc RT. Let me write that correctly. RT delta N. But if you notice in this case here, I have 2 moles of gas on this side, I have 2 moles of gas on this side, so delta N is 0. Well, if delta N is 0, then this whole term turns into 1. So we just know that the Kp equals the Kc, so therefore Kp has exactly the same value as the Kc. No calculations involved. Now part F. At 1000 Kelvin, the value of Kc for the reaction is 2.6. Now they're saying this is a different temperature, so at a different temperature we have a different value for K, and that's fine. In an experiment, 0.75 moles of HI, 0.1 mole of IH2, 0.5 moles of I2 are placed in a 1 liter container. So again, that's convenient. These numbers of moles can also be used as molarities because of the fact it's a 1 liter container. They're allowed to reach equilibrium. Determine whether the equilibrium concentration of the HI, so now we're thinking about HI, turns into H2 plus I2. So we say for this question, what's happening to the HI? Is it going to be greater than, less than, or equal to your initial concentrations? Justify your answer. What I'd like to do for this then is, are we talking about this reaction shifting to the left, or is it going to shift to the right? But we got to give our answer in terms of HI. Now this is a Q problem. So if we have values, all we have to do is substitute them back into our K expression, but we're going to call it Q because we're not using equilibrium values. So my H2 concentration from the reading is 0.1. My I2 concentration, looking carefully at the reading, is 0.5. And my HI concentration is 0.75. Okay, and that's going to be squared. And when I do all that, I get a value of 0.8888 repeating. So I'm going to turn that into 8.9 times 10 to the negative 2. Now that's my Q, and my K, okay, is 2.6 times 10 to the minus 2. So my Q is greater than my K. So Q is greater than my K. Now what does that tell me? That tells me, since Q and K are products over reactants, if my Q is greater than my K, that means my product number is greater than my reactant number that I need for equilibrium. So compared to my constant, my equilibrium constant, which was 2.6 times 10 to the, which was 2.6 times 10 to the minus 2, and I have 8.9 times 10 to the minus 2, then I know that my too many products. So if I have too many products, I'm going to have to switch from my products back to my reactants, and therefore, answering the question, my HI concentration will be greater, if I make some of that, when I reach equilibrium, greater than my initial values. So the answer over here is greater than what was before. Now one thing I've heard people say is they look at this number here and they say, oh, okay, that is a nice small number, okay, so therefore this reaction is going to be reactant favored. And that is not the way to use your Q. Okay, you can't say, if I said my K value, okay, let's go back here a little bit, my K value is 2.6 times 10 minus 2, then I would say, yes, I agree, that means this is a reactant favored reaction, but that's not what we're talking about. we're saying how is my Q compared to my K, and my Q is even greater than my K. Okay, my Q is greater than my K, so therefore I know I have to shift to the left in order to reduce my number of products and make more reactants in order to reach equilibrium. So when we're predicting, you have to see how does Q relate to K, not what is Q like just as it is. And that's problem 1.